Good evening, everyone. So, as you know, today is our topic about corrosion. First of all, I would like to introduce myself a little bit. And my name is Emilya Abdullayeva. I was born and grown up in Baku. I graduated from State Oil Academy, Azerbaijan, and as a chemical engineer for oil and gas industry. I had bachelor and master degree from the same university. Then I started my work experience in Academy of Sciences at the Institute of Petrochemical Processes. And I made my PhD at the same institution. My subject was corrosion inhibitors and biocides for oil and gas industry. And I have 15 years experience on oil and gas industry, a part of scientific experience. I worked as an offshore and abroad experience. I have 2 years experience in Qatar as account manager, and I'm almost 5 years here in Oman as a CHEMinar account manager and senior corrosion engineer. Okay. So, what's a corrosion? Today's our topic is the corrosion phenomenon and oilfield corrosion problems. So, definition of corrosion: corrosion is deterioration of substance or its properties because of a reaction with its environment. I like this statement from corrosion is the most democratic of all processes. It affects everyone everywhere, from driver, bicycle to the refinery operator. So for beginning, I will talk a little bit about corrosion mechanism, corrosion reactions, and parameters which affect corrosion. Then I'll share with you some experiences from oilfield industry. So why corrosion occurs? First of all, it's thermodynamically favorable because it's not stable condition and sorry, 1 minute. Because it's corrosion reaction is a thermodynamical instability of metals in relation of water, air, and oxidizing reagents, compounded state, corrosion products being formed from the pure metals and energy being released in the process. It's consequences of second law thermodynamics, which describes how a system of localized energy will always move towards a state of low energy, dispersing the energy difference into surroundings. In this case, system iron atoms arranged in a lattice structure. It means metallic iron structure reacting with oxygen in the air and form iron oxide. The energy contained in the lattice bonds within the metallic iron and the double bonds holding the oxygen molecules together is higher than energy of the bonds within the reaction. Product rust, which is iron oxide. By talking now about atmospheric corrosion, which is most generally spread in all over the industry and in our daily life. This is demonstrated by the fact that oxidation of iron during the process of rusting releases the difference in energy into the surrounding environment. As heat, the reaction of rusting is exothermic. Rusting is so slow that the release of heat is not noticeable. We can't measure and we can't feel it without very sensitive equipment. So rusting is analogous to combustion of iron, except that at ambient temperature, the reaction is very much slowed down and the rate release of heat is very small. So, basic of corrosion cells, how it's happening in small part of metal. Corrosion reaction involve the transfer of charge between the metal and electrolyte, which is electrochemical nature. And for corrosion should exist this components, as anode, cathode, metallic electrical connection between the anode and cathode, and electrolyte. At the anode, oxidation occurs and cations enter the electrolyte. At the cathode, produced from anodic reaction, consumed reduction reactions. Oxidation of iron and reduction of water you see in this slide. The reduction is shown without a presence of oxygen. And for the reaction to proceed, the anode and cathode must be electronically connected with pipe or with wire, and in contact with an electrolyte, which is usually some fluid or some metallic, which is some fluid. And it's important to note that electrolyte associated with this corrosion reaction need not be a bulk solution. Often only a thin condensed film of moisture is sufficient to corrosion occur. So which factors can affect corrosivity? This is mainly about industry. This is metallurgy, materials of vessels, water chemistry, oil chemistry, solids and emulsifiers, velocity, microbiological activity, temperature, pressure, dissolved gas. And in this slide, you see a small chart in right bottom. This is about process conditions. This is a matrix of high pressure and high temperature operation, and how severe corrosion can appear. It's, by abbreviation, this is high pressure, extremely high temperature, and high upper high pressure and extremely high temperature. And you can see red corner where is extremely high pressure, extremely high temperature conditions, where is severe conditions for corrosion. So forms of corrosion. In this discussion, we will not talk too deeply about forms of corrosion because it's very big subject and need to devote it to separate webinars. Even I see not one, few webinars. So we will talk about this briefly. If you have a question, you can direct me after. So too many forms of corrosion, but mainly we are dividing corrosion forms to two parts. It's uniform and localized corrosion. So uniform and localized corrosion. The anodic and cathodic reaction can either take place statistically distributed all over the surface, leading to uniform corrosion. And uniform or general corrosion is a metal loss that proceed more or less evenly over the surface of metal or a large fraction of material. During uniform corrosion, local anodes and cathodes don't become fixed. This form corrosion can be identified by visual examination of surface, metal surface, and it's recognized by an overall roughening of the surface. Because uniform corrosion occurs over a large area, it's more easily detected from outside of the pipe using ultrasonic measurements than isolated fittings. So here I just touched one point which we will talk later about inspection techniques. We'll talk about this later for further slides. Uniform corrosion can occur in isolated location along a pipeline or vessels due to an isolated environment. Localized corrosion is identified by small discrete sites of metal loss at fixed anodes. You see in bottom of right bottom of slide the example of localized corrosion, and you see pins, small holes. This is mainly anode area of corrosion. We'll talk about localized corrosion mechanism later. And metal surfaces surrounded areas of localized corrosion show minor or apparent attack. Also, pitting can occur within areas of general corrosion as well. So it's like carbon dioxide, oxygen, microorganism, chlorides attack. With all of these mediums, we are experiencing pitting corrosion. So as I told you, there are many types of corrosion, and uniform and localized corrosion, they have different forms. It's galvanic or tool metal corrosion, crevice corrosion, pittings, intergranular corrosion, selective leaching of parting, erosion corrosion, stress corrosion. And also, because in oil field we face very frequently with sweet and sour mediums, which is affecting pH of fluid and causing metal attack. And because of this media dissolved gas, if it's acid dissolved gas, we call this sour. If it's other gases like CO2, oxygen, some hydrocarbons, and organic acids, we call this sweet gases. So I want to talk now for some examples of localized corrosion. Why one of the most popular corrosion type is microbiological corrosion. Microbiology influenced corrosion. This is like known terms in industry and in science. You can face in some books microbiology induced corrosion. Usually NICE using induced corrosion terms. And this is a deterioration of metal due to presence of and activity of microorganisms, bacteria, fungus, algae, and also products, because of products metabolism of bacteria. Corrosion associated with bacteria is usually pit corrosion. You see some examples in this slide. So what types of pit corrosions cause bacteria? This is sulfide reducing bacteria, iron oxidizing bacteria, acid producing bacteria, sulfur oxidizing bacteria, manganese oxidizing bacteria, slime forming bacteria. So as you see from these photos, it's like an example of morphology of MIC. Sometimes when we want just define corrosion problems, we are looking metal surface. This is like just appearance of metal, just observation. And by morphology, we can, I'm not telling that it's defining corrosion type, but we can tell what type of corrosion appears here, but it's not proved each time. You see from this photo like a double ring, pins like a double ring. It means that this is like pitting with flat bottom, and top hole is, top ring is bigger diameter, and then you see a smaller bottom. That's why from top surface you see like a double ring. And usually pittings of MIC is flat bottom. But again, I want to repeat that this is not only signs of MIC. I know from my experience, few times I saw a photo, even I see metal, and I was sure this is MIC, but bacteria results showing no bacteria. So we can't rely on the morphology to define the corrosion type. So aside from acids, the microorganism may also produce alcohols, ammonia, CO2, or H2S, which is sulfide-reducing bacteria, most famous one, and most problematic. Microorganisms can accumulate anywhere, mainly bottom of line, stagnant areas. They may be more prevalent in low flow and stagnant conditions, surface conditions at wells, can also create localized environment conducive to biofilm establishment. Bacteria can produce polymeric material, creates a protective environment, facilitates the flow of nutrients and the removal of waste products, sometimes function to enable symbiotic relationship. So what is this? We call this biofilm, and usually most strong biofilm created by EP-GHP and GHP bacteria, which is acid-producing general heterotrophic bacteria. SRB bacteria causing severe corrosion, but biofilm of this bacteria is usually very weak. They are usually EP-GHP biofilm accommodate SRB, and when we see combination both of this bacteria, if we see its existing system, both types of bacteria, it's a we need to flag it, because SRB can be accommodated by EP-GHP biofilm, which is very strong and sticky stuff. The polymeric material helps create a localized corrosion environment and promotes bacteria growth, which I told, which could make it more difficult to mitigate the corrosion. And factors that promote the occurrence of MIC include low velocity, deposit accumulation, high water cuts, and increased bacterial levels. This is about MIC, microbiologically induced corrosion. Next corrosion type is galvanic corrosion, when two types of metal in contact with each other. Galvanic corrosion is a mechanism resulted from metallic coupling of two dissimilar metals. Galvanic couples exposed an electrolyte mechanism driven by potential difference between the two dissimilar metals. When coupled electronically, the material with the more negative potential acts as an anode and corrodes, while the material with more positive potential acts as anode. As we see from previous slides, when I show you mechanism of corrosion, usually fittings is